All right. Horizontal motion and friction. This is where we left off with. Okay, this is section 11. It's on page 22 on my notes packet. Okay. Um, and the way that it works, okay, is just briefly talking about some friction stuff. Okay, I have to rearrange some stuff on my desk here. Okay, static friction, right? Hopefully you remember what static friction is. Static friction is the friction that acts, friction acting to prevent sliding. Okay? It doesn't prevent, oh, sorry, sliding from beginning. Okay? It's specifically sliding. It's important to note that it prevents sliding. Okay? Um, specifically sliding, right? That's really important, okay? It doesn't just oppose motion, it opposes sliding specifically. And the formula for this is F sub Fs has to be less than or equal to mu sub S times F normal. And that's the big thing here is that it's less than or equal to, it's not equal to mu sub S F normal. I hope you remember that static friction has a threshold, right? Static friction has a threshold, and when you beat that threshold, then the friction breaks, and you're able to actually push the object. Okay, and mu sub S, okay, is the coefficient of static friction. Okay, I just realized I forgot to put the light on here. Okay, and because that sometimes causes it to be a little bit easier to see, or sometimes um, it sometimes it causes it easier to see, and sometimes it prevents like the color from shifting a ton here. Okay, okay. Kinetic friction is the other type of friction. This is probably the more popular one. Okay, it's the friction that acts. Okay, the while sliding is occurring. Okay, so this happens while sliding is happening. Okay, this is like, for example, popular example is if you rub your hands together, right? You're causing kinetic friction between your hands. Okay, this would be kinetic friction. Okay, kinetic friction is equal to mu sub k times normal force. So you're just doing, you're just using the kinetic coefficient now. That's what mu sub k is. It's the coefficient of kinetic friction. Okay. Okay. And there's an important condition that you need to know, okay? An important condition for the coefficients of friction is simply that they both have to be between 0 and 1, but more importantly, kinetic friction coefficient is lower than the static friction coefficient. So in that case, so with that being said, static friction is always greater than kinetic friction for any two objects, okay? Okay, if a car initially moving at 40 meters per second skids to stop in 100 meters, what coefficient of friction is there between the tires and the roadway? Would it be static or kinetic? Okay. Well, let's first solve out the problem. Okay, my first step here is going to be to get the acceleration because, right, if there's acceleration, there has to be a force, right? So I'm going to get the acceleration. Okay. So I'm going to use the time independent. You notice that we don't have any. Notice that we don't have any time, right? So I'm using the no time equation. V squared equals 2ax plus v naught squared. Okay. And what we should recognize is that the final velocity cancels out to zero because again, it's slowing down to rest. So final velocity should be zero. So you get 0 equals 2ax plus v naught squared. Okay. And then if you subtract v naught squared from both sides, you would get negative v naught squared equals 2ax. Okay. Um, and now all you got to do is get a by itself. You've got everything in here. It's initially moving at 40, so it's negative 40 squared equals 2. We don't know the acceleration. And then the x, the distance is 100 meters. So then we could calculate it out like that. Okay. And if you do that right, you're going to get negative 1600 equals 200a. And then you would divide the 200 on both sides, okay? And you would end up getting the A should be equal to 8 meters per second squared. It's technically negative 8 meters per second squared, okay, because it's slowing down, okay. So really quickly, I'm just going to show you what should the forces look like on the car. That's my step 2 is draw forces, okay. Well, on the car, right, I'm going to draw this dot right here. I've got normal force going up. I've got mg going down. I don't care about those. I really don't, okay? But we do have friction, okay? So what's happening, right, is there shouldn't be any force going forward because we're not told that there's a force going forward. There should just be the friction force opposing, okay? My third step, okay, is going to be set F net equal to ma. So use Newton's second law, okay? Use the force of friction equals ma, right? Because that's our net force in the horizontal direction. So then it would be mu F sub n equals ma. Maybe I do care a little bit about the normal force now because I do need to get it now. Well, what you should notice is that F sub n, especially for an object on like a flat roadway, is just going to be mu times mg, okay, equals ma. And then take out the m's, because you've got that on both sides. So it would just be mu times g equals a. Okay? And then all you got to do for the final step to close everything out in step 4 is to solve for mu. Okay? And that's really easy. All you got to do is divide by g. So you would get mu equals the acceleration, which we solved was 8, divided by 10, which is g. And so you should end up getting a coefficient of 0.8. Okay? That's a coefficient of friction. Is this kinetic or is it static? It has to be kinetic, and I'll tell you why. Because sliding has begun. Kinetic, okay? Because sliding has begun. Okay, if the car skids to a stop, then that means that sliding has occurred, right? We learned last year that you need static friction to get the wheels to turn, but kinetic friction would cause the wheels to slide and skid. Okay, and you don't want that. Okay, I believe that's it for horizontal motion. Yep, that's it for horizontal motion. So live, laugh, love. Okay.